If you watch a massive physical collision in space, you witness the transfer of energy, the resistance of mass, and the pull of gravity. To construct the pure geometry of motion, we strip away the physical reality entirely. Kinematics isolates the temporal and spatial evolution of a system from the dynamic forces that precipitate movement, like mass, inertia, and energetic inputs. The discipline operates exclusively within 5 parameters: position, distance, velocity, acceleration, and time. This animated diagram shows the core technological construct born from those 5 variables, the continuous, infinitely divisible mathematical trajectory. It specifies the precise permissible states of a physical system moving through an empty coordinate space. We rely on this mathematics to map complex mechanisms in modern AI robotics and to navigate relativistic boundaries. Yet the concept of a smooth, perfectly continuous path is an artificial assumption regarding the nature of space. The human effort to conceptualize motion as an abstract, measurable phenomenon began long before the invention of Cartesian planes or calculus. It finds its earliest systematic expression in the philosophical treatises of ancient India. Applying this geometric abstraction to subatomic particles results in a loss of mathematical determinacy, revealing the limits of our classical models. Tracing the history of kinematics shows how humanity engineered a specific conceptual lens to translate the phenomenon of change into rigorous, predictable logic. Between the 6th and 2nd centuries BCE, scholars in ancient India formulated a systematic, realist ontology of the physical universe, known as the Vaisheshika school. The philosopher Kanada constructed a universe from eternal, indivisible atoms. Within this framework, he classified motion, termed karma, not as an independent physical substance, but as a transient phenomenon that strictly inheres within those finite atoms. This diagram shows Kanada's logically exhaustive taxonomy of observable physical changes. He derived exactly 5 distinct directional states: upward translation against gravity, downward translation aligned with gravity, spatial contraction, spatial expansion, and a general state of locomotion for curvilinear paths. Because motion cannot permeate infinite, immaterial spaces like ether or time, the ancient scholars concluded that every occurrence is temporary. It requires a definitive physical cause to initiate and sustain it. Later commentaries linked these isolated motions to underlying forces. They identified gurutva, gravity, as an inherent quality of earth and water atoms that causes downward translation when no counteracting physical support exists. The Vaiśeṣika Sūtra encoded robust principles of mechanical causality. A core axiom dictates that an effect strictly arises from a cause, explicitly declaring that motion never occurs without an applied force. The text Vega Nimitta Visheshat Karmono Jayate outlines how a change in a body's state of motion is born from an external force. Later scholars augmented this with the concept of momentum, noting an object maintains uniform, straight-line motion until counteracted by friction. Another sutra recognizes action and reaction as mutually opposing forces, asserting that every action is countered with an equal and opposite reaction upon collision. These ancient scholars derived the same fundamental relationships between force and motion that would eventually anchor Newtonian physics. These theoretical principles eventually found practical application within the astronomical traditions of ancient India. In the 12th century, the mathematician Bhāskara II faced the challenge of predicting precise planetary positions. This required calculating non-uniform, continuously changing orbital motion. This elliptical orbit model illustrates Bhāskara's problem: fluctuating transit speed. To solve for instantaneous velocity, he measured displacement over an infinitesimal time interval, a trility. As this interval shrinks to a secant line, Bhāskara proved velocity vanishes to exactly 0 at the orbital extrema. By proving that the differential coefficient of the equation equals 0 at this intermediate position, Bhāskara formulated an early iteration of Rolle's theorem. This captured the continuous mathematics of kinematics centuries before European contemporaries formalized the calculus. Mastering the infinitesimal derivative was the definitive leap required to transform kinematics from descriptive philosophy into a predictive engineering tool.
Classical mathematics takes Bhāskara's infinitesimal derivative and expands it into an entire spectrum of continuous temporal measurements. Taking the first time derivative of a position vector yields velocity. The second derivative yields acceleration, providing the core bridge to force dynamics under Newtonian mechanics.
Real-world engineering, however, requires analyzing the rate at which acceleration itself changes. This third derivative is known as jerk. In modern mechanical design, abrupt and violent shifts in acceleration introduce transient forces that cause severe mechanical fatigue. To minimize these vibrations, engineers calculate even higher-order derivatives, formally classified as jounce, the fifth derivative crackle, and the sixth pop. When kinematic analysis requires evaluating the intrinsic geometric shape of a path independent of the transit speed, engineers replace time entirely with the arc length parameter. The Frenet Serret frame maps this space curve using a three-axis triad attached to the particle. At a bend, the tangent vector tracks velocity, and the principal normal tracks the curve's bend. As the path twists in 3D, the binormal vector calculates spatial torsion. This moving trihedron perfectly describes a single continuous point in Euclidean space. But when engineers attempt to scale this coordinate geometry to complex multi-link machines, the local constraints encounter mathematical singularities. In mechanical engineering, kinematics transitions from describing isolated particles to mapping the interconnected motion of multi-link rigid bodies, such as robotic manipulators. For decades, the dominant kinematic representation in robotics was the Denevit-Hartenberg convention. It systematically defined motion by assigning local coordinate frames onto every successive joint. The flaw in the DH framework is its strict reliance on local assignment rules. Specifically, the parameters must align along the intersecting common normal between adjacent axes. This visualization of a multi-link robotic arm demonstrates the mechanical consequence. When joint axes run perfectly parallel, the common normal becomes infinitely non-unique. Under these parallel conditions, microscopic machining errors or sensor noise cause the mathematical parameters to fluctuate, resulting in unpredictable control instability. Modern robotic kinematics abandoned the DH convention and its local frame constraints entirely. The solution was found in screw theory. This animated diagram maps the geometric theorem underlying screw theory. It proves that any rigid body displacement, no matter how complex, is equivalent to a simultaneous rotation and translation along one unique global spatial axis. The underlying topology of this global framework represents the finite position and orientation of a robot using the special Euclidean Lie group SE3, while its instantaneous spatial velocity is encoded in the corresponding Lie algebra. By utilizing the exponential map to smoothly integrate constant velocity twists, the system traces a seamless mathematical manifold. This eliminates singularity traps and natively enables advanced SE3 equivariant deep learning architectures in artificial intelligence. Operating within these Lie manifolds represents the absolute mathematical perfection of the continuous trajectory, allowing for the coordinate invariant control necessary to orchestrate robotic automation. Every model discussed so far relies on a single foundational assumption. The universe is an infinitely continuous, smoothly divisible space. At the subatomic boundary, the assumption of a smooth path reaches its physical limit. In 1925, Werner Heisenberg authored his Umdeutung paper. Confronting the failure of classical orbital models, he proposed a doctrine. Physical theory must exclude unobservable quantities. Because an electron's exact position and velocity cannot be observed without disturbing the system, Heisenberg discarded the concept of the continuous orbital trajectory. He replaced classical continuous functions of position and motion with discrete, non-commutative mathematical arrays that represent the initial and final states of quantum transitions. This diagram illustrates the canonical commutation relation. In algebraic quantum kinematics, the multiplication of conjugate variables depends strictly on the sequence of operation, yielding this non-commutative quantum matrix formula. This shift from geometric paths to non-commutative operator spectra shows that the continuous trajectory is a mathematical model limited by the scale of the system. From the logical realism of Vaiśeṣika atomic theory to the smooth Lie manifolds guiding artificial intelligence, the evolution of kinematics spans millennia.
The discipline derives its analytical power by deliberately separating the geometry of change from the dynamic physical forces that cause it. Ultimately, kinematics functions as a scale-dependent lens, the essential mathematical syntax we require to translate the raw chaos of physical motion into human understanding.